Hi there, and welcome to our Chapter 10 lecture video. Today we're going to focus on chemical bonding. With that, we're going to mainly look at Lewis structures, which is how we connect covalent bonds. We can show these for ionic bonds, but it's not as important and kind of just a redundancy. We're going to look at molecular geometry, which is how we adapt two-dimensional structures to the actual three-dimensional structures. Luckily, a lot of the molecules we care about are actually two-dimensional. They're perfectly flat. There are going to be 5 molecular geometries that I force you to memorize. You're going to need to know the bond angles of some of them and basically just how they look and how to draw them on paper. Electronegativity is something that's very important to this lecture, but we've been talking about it for a while, so hopefully you're getting used to it. And then polarity. We're going to use electronegativity to kind of figure out polarity, which is the difference in how covalent bonds hold their electrons. So if you have something like molecular oxygen, oxygen bonded oxygen, there's no difference in electronegativity. There is no polarity. Something like, hydrogen chloride, there's a big difference in electronegativity. We have a large polarity or a very polar bond, as we're going to refer to it. So first things first is we're going to talk about our bonding theories. There's a whole bunch of them out there. We'll show a few. We've shown some at this point. The most important one is going to be the Lewis model, which is after the chemist who came up with it. I don't know his name. You don't need to know his name. His last name is Lewis. That's about all I care. This formula or model uses dots of the valence electrons to represent what's going on with the molecules. We can take different elements and their Lewis dot structures, combine them to make molecular Lewis structures. Typically, we'll only look at Lewis structures of molecules because individual atoms are a little redundant and simple, but we will show them for the sake of it. So we count our valence electrons. We can get this from the periodic table. We can count it just in the group number, or we can remember that our group numbers relate to the actual number of valence electrons. We can either count across, 1, 2, until we get to 8. There's 8 electrons in the main group. That's why we have our octet rule. Make sure you're reviewing your chapter 9 if you haven't already. But for Lewis structures, we're only going to show the 8 electrons of the main group. We'll arrange these valence electrons around the atom in a symmetrical fashion. It doesn't matter how we do this, but the rule is that we pair single electrons first until we get to 4, and then we start pairing them up. So single electrons first, then the pairs after we get to 5, 6, 7, and 8. 8 will have 2 pairs around each cardinal direction, up, down, left, right, north, south, east, west, however you like to think about it. And so, like I said, we place them evenly around, single first and then pairs, just spelled out in words right here. This would be the electron dot diagrams for the second row of the periodic table, but the first full main group row. The first row of the periodic table only has hydrogen and helium, just the S block. We sometimes treat hydrogen like P block, sometimes we treat it like S block. It's kind of dependent on what's convenient for us since they're the exception. But the rest of the main group has 8 valence electrons, 2 from the S orbital, 6 from the P orbital. We have their octet. What you'll notice is that phosphorus, which is in the same group as nitrogen, have identical Lewis structures. This is because elements of the same group have the same number of valence electrons. And so every element within a group will have the same Lewis dot structure. So if you memorize these 8 Lewis structures, you now know all the Lewis structures for every element in the main group. We don't do this for the transition metals and the lanthanide actinides because they have, the 18 electron and the 32 electron rules. That would be really cumbersome to draw all those around. And it's just not a useful mechanism for those elements. So we just do this for the main group. Now, we can do this for ionic compounds, but we tend to do this for covalent bonds. It's kind of boring for ionic compounds, but we'll go over it. You'll definitely see it at some point in your time. I always see it and then I forget about it because it's not a useful tool. But we share our electrons in the case of covalent compounds. In the case of ionic compounds, we completely give all of the valence electrons to the anion and have an empty Lewis dot structure for the cation. Now we'll go back to our rule of thumb that when a nonmetal bonds to a metal, the nonmetal will take the electrons from the metal. We'll get a cation for the metal and an anion for the nonmetal. We can represent this with our Lewis structures like such. Our dot structures of the pure elements are just however many valence electrons or whatever group number they're in. Group 1 has 1 electron. Group 17 or 7A has 7 electrons. Potassium is less electronegative, so it'll give up its electron to chlorine. Chlorine will take a minus charge with a full current valence shell. Potassium gave up its electron and has an empty current valence shell. Its previous valence shell is filled, but now we represent it being empty. Just a little bit more convenient to show the positive and minus. Empty, full valence shell. So we can do this with, polyatomic ions and elements. So magnesium has 2 plus, oxygen has 2 minus. Magnesium is just giving up the 2 electrons to oxygen. We draw it just the same. If we have sodium sulfide, where it's a, single ionic charge to a diatomic charge, 2 negative charges to 1 positive charge, we're going to need 2 sodiums to cancel that out. If you want to stack them vertically, 1 sodium on top, sulfur in the middle, sodium on bottom, great. Typically, we do this left to right, just takes up less space, much easier for text generation. The important thing is that we keep everything symmetrically spaced. So, moving on to covalent compounds, these are compounds that share their electrons rather than completely taking or giving. And so, these are between elements of the same block. So, we'll have P block to P block, S block to S block, D block to D block, F block to F block, so forth and so on. We're only going to deal with elements from the P block that are bonding to each other. And so, like I mentioned before, hydrogen kind of gets some special treatment when it works for us as a P block element, even though it's technically an S block element. So we have hydrogen and oxygen bonding together. If you have 2 hydrogens bonding to oxygen, we get water. If you just have 1 hydrogen bonding to oxygen, you get hydroxide, which is one of our polyatomics. And so in order for oxygen to have its full octet, it would have to have an extra electron if it didn't have, the hydrogen donating that electron. And so that's what would give us the negative charge in hydroxide. We want to note that hydrogen is an exception and that it has a duet, whereas every other element that we talk about is going to have an octet. If something has less than its, octet, we call this hypovalent. If something has more than its octet, we refer to this as hypervalent. We'll see a few examples of this. I'm not going to try to give, exam questions on this or anything like this, but you will see it. Sulfate and phosphate are examples of hypervalent polyatomics. When we look at electrons that are between elements, we refer to these as bonding electrons or a bonding pair of electrons. You need at least 2 electrons to actually form a bond. And so these electrons that are not between elements, we refer to as lone pairs or non-bonding pairs. Again, chemistry, we have all these synonymous terms. It's good that you're familiar with a whole bunch of them. You only need to communicate in one way or another. You can just think of these as bonds and lone pairs. That's typically how we do it at the introductory level, but calling these bonding pairs, non-bonding pairs is a little bit more formal and correct. If we have just a single electron, not a lone pair, that would be called a free radical. We'll see an example of that, but I'm not going to ask you about these. In general, if you have an odd number of electrons in a compound, it's very likely that you're going to have some type of free radical species. So we can use the lines or the dots. So we can use 2 dots in between here or a single line. We can also use a bar or a straight line to represent the lone pairs. So any pair of electrons can be represented by a line or a dash. And so chlorine is nice and easy. It has 1 unpaired electron. We can pair these electrons up and get a single bond or a dash between them. This predicts that there's a single bond between chlorine and chlorine when you have molecular chlorine. This is true for all of the halogens. As we move across the periodic table to oxygen, nitrogen, they tend to make more and more bonds. So the halogens tend to like to make 1 single bond. You'll never see a halogen or hydrogen that makes more than 1 bond. Oxygen, the next element over, group 16 or 6A, has 6 valence electrons instead of 7 valence electrons. It's going to like to make 2 bonds since it wants to share 2 extra electrons. Chlorine only needs to share 1 pair of electrons. Oxygen needs to share 2 pairs of electrons in most cases if it wants to be neutral. Nitrogen needs to make 3 bonds. Carbon needs to make 4 bonds. Group 13 is an exception. We've talked about it when we did our Lewis or our electron configurations. So hydrogen, it's a duet. We said it tends to only make 1 bond. This also means that halogens and hydrogen can never be our central atom. We're going to talk about this when we get into more complicated Lewis structures, but for now, just remember that when we have hydrogen or halogens, they can't be a central atom. If we have 2 atoms, neither of them have to be a central atom. They're both terminal. So oxygen has an issue. I mentioned this already, but it doesn't have enough that if it just shares a single pair, so it's going to want to share 2 pairs of electrons in order for both element to have its octet. Nitrogen is one further. It has 2 missing electrons on each nitrogen if we only share 1 pair. So each nitrogen is going to share 1 additional pair or 3 total pairs entire. So we call this a triple bond. The more bonding you have between individual elements, the closer those are together, or the shorter the bond length, the stronger the bond is. A single bond is not half as strong as a double bond, or a double bond is not twice as strong, and a triple bond is not 3 times as strong as a single bond. A single bond is the biggest change in distance between atoms. Then the double bond is just like adding a little bit extra, and a triple bond is just a tiny little bit more. They're not multiplicative. So in singly bonded oxygen, you would see that it's 148 picometers, about 150. And for doubly bonded oxygen, like in molecular oxygen, you see 121 ppm. So about a 30 ppm shift. And then nitrogen, which is a different element, so it's not an exact comparison, apples to apples. Again, this is a little apples to oranges because we were talking about oxygen here and nitrogen here. But a nitrogen-nitrogen triple bond is 110 picometers. So not a huge difference between a double and triple. And that's consistent with what's actually occurring, is that the single bond is the biggest impact. A double bond is more impactful than a triple bond. And then we have quadruple and quintuple bonds that only exist in the transition metals and lanthanide actinides. We're not going to talk about those. But every additional bond is stronger, but by a diminishing amount. So we have this diminishing returns when we're doing multiple bondings. So we have a whole bunch of rules, and there's different variations for how we draw Lewis structures. I'm going to mainly focus on what the book says, because that's what the slides are based off. But I will tell you my method, which I believe is a little bit superior because it gives you a better Lewis structure when you start having exception cases like hypervalency or hypovalency. So keep that in mind. Either method will give you correct Lewis structures. One will have more caveats, so to speak, and that will be the book method that we're going to primarily go over. After we go over our first Lewis structure or two, I'll mention my method that's a little bit more straightforward, I think. So in general, we need to figure out what our central atom is. This is going to be the atom that you have the least amount of. So if I have, 10 of this atom, 5 of this atom, 3 of this atom, and only 1 of a certain atom, whatever that 1 is likely going to be your central atom, unless you're dealing with big organic molecules, and we're not going to do anything like that. But whichever atom you have the least of and is the least electronegative. So if I have, 1 carbon, 1 oxygen, and a bunch of hydrogens, well, carbon's going to be the central atom because it's less electronegative. Oxygen's going to prefer to be on the terminal because it wants to steal electrons from carbon. Carbon's happy being in the middle, kind of divvying up its electrons, so to speak. So we want to keep molecules symmetric. We don't really care about the geometries at this point, but we will get into that. We just want to keep them symmetric on the, up, down, left, and right positions. You want to calculate the total number of electrons. You get this from the group number. We're only concerned with valence electrons, not total electrons. So if I had, oxygen, O2, molecular oxygen, I would take 6 electrons from the first oxygen, 6 electrons from the second oxygen, because they only have 6 total valence electrons, and I would have a total of 12 electrons in the molecular Lewis structure. Polyatomics, if they have a plus charge, you need to take away electron. Take it away from the least electronegative element. If you have a negative charge, add an electron. Just add it to the most electronegative element. Then form bonds between the central atom and the terminal atoms and fill in the rest of the electrons. If you have to, apply double bonds and triple bonds to give everything its octet. But sometimes this will have some issues. Again, make sure that the total number of electrons and bonds adds up to what it ought to. Everything should have an octet, unless you know that it's going to be hypo or hypervalent. And everything should have the total number of electrons so that it's a neutral species, unless otherwise specified. So this works really well when we have nice, simple molecules. We'll put, carbon in the central because there's one carbon to 4 chlorines. We'll put one bond between all of these, and we'll get this structure. We'll then fill in the rest of the electrons around. This is great. What I would recommend is that you fill in the valence electrons around each given element. So give chlorine its 7 electrons and have the unpaired electron facing carbon. Give carbon its 4 valence electrons and then pair the unpaired electrons. I'll show this in lab and, in office hours if you come by. I find this to be a much more convenient approach. Both will get you the correct answer. I just like to put up the valence electrons instead of putting the electrons around systematically. I like to give the elements what they actually have because that's a little bit more accurate to what's going on. You're not just taking all the electrons from every single element and divvying them out however you feel like. No, certain elements have certain electrons, and those electrons are associated with those elements. So I prefer to do it that way, but the books method is probably the more common method online that I see. So feel free to use this method. It will get you the correct answer. So we can do this with CO2. Evenly disperse everything. Carbon's going to be the central atom. Oxygen's going to be the terminal atoms. Line or linear geometry is the easiest way to space these out. You wouldn't want to put them at a right angle. That would be awkward. It wouldn't be quite symmetrical. So we'll count our electrons, place bonds in between carbon and oxygen. Then we'll fill in extra multiple bonds, or double bonds in this case, to give carbon its octet, because in this case, carbon only has a quartet, 4 electrons. It's half of its valence shell is filled, so it needs to take 2 electrons additional from each oxygen. So we can draw polyatomics. We went over how we do ionics. We kind of do the same thing with polyatomics with their pairs. So cyanide is a polyatomic. We'd give carbon its 4 electrons, nitrogen its 5 electrons. It has a minus charge, so we add 1 extra electron. We want to put a bracket around this Lewis structure so we represent that it's an ion. Remember when we were doing, sodium chloride and sodium sulfide, we had a naked cation and a bracketed charged anion. Well, same thing here. We're going to show the Lewis structure inside of the bracket, but we need to indicate that it is an ionic charge. Whether you use the dashes or the dot notation, doesn't really matter. Again, fill in electrons between the 2 elements, then fill in, as many as you can, pair them up until you have full octets for all your electrons. So, exceptions. You're not going to see these on exams, but we should talk about them. Free radicals. So, free radicals are unpaired electrons. These are very unstable. There's better to have a lower number of paired electrons than a higher number of unpaired electrons. And this just comes down to the mathematics. Group 13 tends to make septets, and because of this, they tend to have these empty positions. This is actually an empty p orbital when you actually look at the molecular orbital diagrams, but that's not important for this class. That's getting on to more advanced inorganic chemistry classes. But group 13 tends to only have 6 electrons in its valence shell, and so they tend to make these trigonal planar geometries, which is one of the geometries you'll need to know. Sulfur and phosphorus. This is going to be the exception you actually interact with. Not because I'm going to force you to do a whole bunch of stuff with it. It's just because phosphate, sulfate, phosphite, sulfite, sulfuric acid, phosphoric acid, these are all very, very common chemical. Sulfuric acid is the #1 produced chemical in the world. And so we're going to show you these chemicals because it's representative of what's going on out in the world. But sulfur and phosphorus tend to be hypervalent. The book refers to this as expanded octets. There's a whole bunch of ways to rationalize these, but most of them aren't very good. Just it's simpler to say that sometimes sulfur and phosphorus at this stage become hypervalent. If you take more and more classes, you'll actually explain this with the mathematics, but it's not actually breaking the octet. It's just a formalism. So we're now going to move on to resonance structures. Resonance structures are just equivalent structures for the same molecule. If we have double bonds, it's likely that we're going to have a resonance structure, especially if there's some type of asymmetry in the molecule. So in this case, we draw our Lewis structure. Sulfur needs one extra pair of electrons from one of these oxygens. But which oxygen do you pick? There's not a particular answer that actually matters. So it could be this oxygen to the right. It could be this oxygen to the left. And so what we'll show is that either structure, either the double bond on this side or the double bond on this side is correct. And so what's actually happening is this molecule is resonating between these two different hybrid structures. And so 50% of the time it looks like this, 50% of the time it looks like this, and it's just bouncing back and forth between which oxygen has the double bond. This improves the stability of the molecule, and anything that improves stability is something that's going to happen naturally. So carbonate, nitrate, sulfate, phosphate, all of these things where you have oxygen multiply bonded to certain things but only singly bonded to other things, you're going to have a lot of double bonds. If you have only single bonds, you'll never have any resonance structures. So we represent these with a forward and back arrow. If you have a polyatomic, you need to put the brackets, but in this case, we don't need to put the brackets. If you want to be careful, you can put a bracket. It's just a little bit of extra work, but these double-sided arrows are what we use to represent that these resonate to and from each other. VSEPR is how we talk about three-dimensional models. So everything that we've shown has been two-dimensional because we're looking at a two-dimensional screen. We're looking at a two-dimensional whiteboard. Everything that we represent is flat. It's very hard unless you have a ball and stick model kit to actually show things in 3 dimensions. VSEPR is a set of rules and theories and ideas that help us determine what molecules look like. Valence shell, electron pair, repulsion theory basically says that electron groups group together and push each other away. So lone pairs will group together and bonding pairs will group together. The lone pairs exert a stronger force and they kind of distort the geometry a little bit. The electrons in the lone pairs take up more space or take up more force. They're stronger. The bonding electrons are a little bit more satiated, so they get bullied, so to speak, by this. The lone pairs will push away the bonding pairs, and every type of similar electron, lone pairs and lone pairs, bonding pairs and bonding pairs will kind of group together. This is awkward and complicated words. Let's look at it in some pictures. So we have no lone pairs on carbon, but we have oxygen kind of on equal side. This is going to give us a perfectly linear geometry. This is one of the geometries you have to memorize. You're going to have to memorize all the geometries of carbon because it's the most important element for, organic life. We're organic life, so you should know something about carbon. Carbon, when it bonds to 2 things or just one thing, like in the case of carbon monoxide, takes a linear geometry with 180-degree angles between each bond. If something is bonded to one thing, it can only make a line. 3 things, you can have a couple different geometries. We're going to have what's called linear and bent geometries when you're bonded to 3 things. If I don't have any lone pairs on the central atom, I'm going to be linear when I'm bonded to 3 things, or bonded to 2 things. If I'm bonded to one thing, I have to be linear. If carbon is bonded to 3 things instead of 2 things, we get trigonal planar. This has 120-degree angles and is perfectly flat. So this is very easy to represent on a piece of paper. If you have something that is not perfectly symmetrical, like formaldehyde here, the lone pairs on oxygen group up and actually distort this molecule. So instead of being 120, that's the idealized angle. The real angle is 122 between the oxygens and hydrogens, and 116 between the hydrogens. This is because the lone pairs on oxygen force down the bonding pairs of electrons between carbon and hydrogen. The lone pairs are just bullies and they want to take up more room. They push everything else out of its way. They group up and push everything else away. Everything else has to group up so that it doesn't get beaten up so much. So our next geometry, so we've talked about carbon bonded to 1 and 2 things, carbon bonded to 3 things. Now we have carbon bonded to 4 things. This is everything that carbon can do. One central atom bonded to 4 other atoms without any lone pairs gives you a tetrahedral geometry. If it's fully symmetrical in the terminal groups, hydrogen, 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 carbon, 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 just all the same element, we get 109.5 degree bond angles. This perfectly optimizes the distance between every group. We could look at a space filling model as well. These are very useful to see how large things are, what can interact with what, if things bump into each other. Very hard to show on an actual piece of paper by yourself, so you'll never have to do this, but you'll see them in books quite often. Like I mentioned, tetrahedral is such an important shape because it maximizes the angulature between every group. Most of our body is made up of tetrahedral molecules, but that's just the backbone. All the important stuff is actually not the tetrahedral molecules. Everything that makes stuff happen, enzymes, active cavities in the body where stuff goes on, are actually not these tetrahedral sites, but they make up the majority or the bulk of everything. 99% of your DNA is just junk DNA. It's only like less than 1% or something that actually codes for what you are, who you look like. And so same thing with carbon and the body. So our last geometry other than bent that we've already kind of mentioned is the trigonal pyramid. This is what happens when you remove a bonding pair from a tetrahedral molecule. So if you look at the electrons, they'll form a tetrahedral geometry. We call this the electron geometry. The electron geometry is not really important to anything. The molecular geometry is what we care about. And the shape that this molecule takes is a trigonal pyramid. It's essentially the bottom or the base of the tetrahedron. So sorry to jump back and forth, but we have it right here. Bottom of the tetrahedron, lone pairs up top. The bond angles are identical to tetrahedral because this is a tetrahedral molecule. Now, depending on what these terminal groups are, this gets a little bit distorted because if you have really, really big molecules here, carbons and nitrogens, oxygens, huge things that make long chains, these lone pairs can't, exert as strong of a force against multiple things. And so this bond angle can shift very readily if we don't have symmetry in small molecules. Something you don't really need to care about, just the exception case. Our last geometry is bent. And this is when we have some amount of lone pairs and 2 bonding groups. So oxygen has 2 lone pairs and 2 bonding groups. We also saw sulfur dioxide, which had 1 lone pair and 2 bonding groups. It takes a similar geometry. It's just the angle between these 2 terminal groups is slightly different. And that's dependent on electronegativity, atomic size, and electron pairs. So you don't need to know that water forms 109.5 and then sulfur dioxide forms closer to 120 degree angle. You just need to know that they form some sort of bent angle. The reason for that bent angle is the lone pairs. So here's a chart of the geometries you need to know. You don't need to know the bent angles, but you do need to know the idealized angles for linear, trigonal, planar, and tetrahedral. Here are the other ones that you need to know. Again, bent is kind of being redundant since we have bent with 2 lone pairs and bent with 1 lone pair, just more or less degrees of the bent angle. And then our trigonal pyramid, which you need to know as well. So this encompasses water, ammonia, and all the geometries of carbon. These are some of the most important molecules to life and civilization. So I think, and the department thinks, that you should know these molecular geometries. So we can draw these VSEPR structures. I'm not going to make you draw them. I will give you them and expect you to understand them. but I won't make you draw them yourself. That's for, future classes. You'll do a lot of this in organic chemistry. So if you know you're taking organic chemistry, maybe prepare yourself. There will be some practice in the homework, but I'm not going to put it on the exams and quizzes. The way we represent this is using hashed or dashed, which I will typically refer to it as dashed, and wedged lines. The straight lines are in the plane of the board, paper, screen. Hashed is going into the object, wedged is going out towards you. So we can take our geometries and represent them with these bond and dash notations. So for some things, linear, trigonal planar, bent geometries, these are very easy to represent with Lewis structures. However, we need these wedge and dash notations once we get to more three-dimensional geometries. So our last topic of today is going to be polarity and electronegativity. So electronegativity, we've talked about this a lot. Polarity is the application of electronegativity to a bond. So if you have two things bonding to each other, the difference in electronegativity is our polarity. We have this adage that like dissolves like. So oil and water are not the same. The reason for that is water has oxygen and hydrogen bonds, which are very polar. There's a big difference in electronegativity. There's an uneven sharing of those electrons. Whereas in oils and gasoline, you have carbon, hydrogen, and carbon-carbon bonds. Carbon-carbon bonds have no difference in electronegativity, and carbon-hydrogen bonds have very small difference in electronegativity. And so they would rather interact with each other, similar things, than interact with things that are very, very different from them electronically. And so we've talked about electronegativity. It's just the pull on the electron by the nuclei. Fluorine is the most electronegative in the top right corner. Francium is the least electronegative in the bottom left corner. It increases from bottom left to top right. And so we have this idea of a dipole moment. A dipole moment is a separation of charge. A dipole is a separation or two opposite poles. A dipole moment is a moment in time at which you have this separation of charge. We have this in almost all molecules where there's a difference of electronegativity. Sometimes symmetry can cancel out this dipole moment. We'll talk about that. But in general, we don't have that. And so oxygen has a higher electronegativity. It pulls more of the electron density towards it. Hydrogen isn't as strong, but it's able to keep on to some of its electronegativity. It's centered tightly around its nuclei. And then once you get further away, it gets disparate until you get close to oxygen again. So we represent this with partials. This isn't ionic. It's not fully negative and fully positive. It's a partial minus and a partial positive. Anything with a dipole moment is considered covalent. And in order to know whether it's polar covalent or non-polar covalent or ionic, we have to just compare it to a scale. I don't expect you to memorize these scales. So if I ask for this, you'll be given the values. It starts at 4.0. It's defined at fluorine, and then it just drops down according to a mathematical equation that Linus Pauling came up with. So I guess francium is 0.7. I'm not sure if that's francium or cesium because I don't know that he had access to francium when he was alive. It's a very, very radioactive and unstable element. Cesium is a very, very reactive, but not radioactive element. So not sure what 0.7 is in reference to, but 4 is in reference to fluorine. Increases from the bottom left to the top right. That's the most important thing. Here's a scale. So based off cesium, not francium. So I would have to give you a scale like this to show you what the electronegativities are so you could calculate what the difference of electronegativity is, or the delta En as we sometimes refer to it. So we have perfectly covalent or non-polar. The book refers to it as pure covalent bond. It's kind of an awkward way, but I've heard to it as more perfect covalent. This is when two elements of the same type are bonding to each other. So essentially our homo compounds, molecular elements, sulfur, chlorine, oxygen, anything that has the same name as the elemental name. When we have compounds, sodium chloride is an ionic compound. There's a big enough difference in electronegativity that chlorine fully steals the electron, sodium completely gives it up. They stick together by an electrostatic charge interaction that creates a crystal lattice. If this crystal lattice can be disrupted by some type of solvent, partial positives, partial negatives, or even full positives, full negatives, this crystal lattice can dissolve. And so that's what solubility is, and things that dissolve. When we have things that are big differences in polarity, but not quite enough to fully ionize, we have polar covalent bonds. So the halogen acids or hydroacids, hydrogen bonded to some halogen, have pretty big differences in electronegativity, but even hydrogen fluoride does not quite have enough electronegativity to be considered ionic. And so most of the electron density is on the halide or the electronegative atom, but hydrogen is still hanging on to just enough of the electron density for them to be bonded to each other through these shared electrons rather than an electrostatic interaction. Ionic charge, electrostatic. Covalent, actual share, the electrons are binding them together. So here is our definition of what non-polar, polar, and ionic is. You don't need to memorize this, but this is something that I'd give you if you had to answer questions on it. It will absolutely be in the homework, so you might want to reference this chart in Table 2, 10.2. So this is another, I think, a little bit more useful diagram where you can actually see, okay, we're past the ionic scale. We have isolated nuclei. We don't have this molecular species. When we perfectly share, there's no uneven distribution of the electron cloud. When we're polar, there's a distribution of the electron cloud. So polar molecules, polar bond, but you can have polar bonds in nonpolar molecules. So if we have symmetry, like in CO2, carbon and oxygen are polar and are different enough in their electronegativity that their value is greater than 0.4. However, because of the symmetry of oxygen on one side and on the other side, this pulls apart on carbon equal and opposite. Because of this equal and opposite pull, we would call carbon dioxide nonpolar due to symmetry. It has polar bonds, but those polar bonds are in equal and opposite directions, so the pull on carbon is essentially neutralized out. If you have two people with the exact same strength pulling on a rope, that rope isn't moving from one side to the other. If you have an uneven pull, 20 people on one side and one person on the other side, yeah, that one person's going to get pulled that direction, even though he might be stronger. But if we have an even and opposite pull, we get nonpolar molecules with polar bonds. Now here we can see a couple more examples of polar geometries and nonpolar geometries. Tetrahedral, if you have equivalent groups, will give you nonpolar geometry. However, no matter what you have, unless you just have nonpolar bonds, bent and trigonal pyramidal will give you polar molecules. So that's everything that we're covering today. We mainly focused on the Lewis models. We introduced the molecular shapes with the VSEPR theory. You're not going to be responsible for producing these, but you need to understand them. You're going to be responsible for producing Lewis models. There won't be any challenge questions from this chapter, but you're going to have a lot of Lewis structures coming up and in future chapters and exams. Electronegativity has been a topic of the entire course, so hopefully none of this is really new, but increases from the bottom left and up to the top right. Starts with francium, ends with fluorine. We can use this electronegativity and symmetry arguments to determine what the polarity of the molecule is. Remember, solubility is just determined by polarity. Similar polarity things will dissolve into each other, whereas different polarity things will not dissolve into each other. Oil sitting on water, different polarities will not mix. So that will cover it for our Chapter 10 lecture. If you have any questions on any of these topics, please make sure to reach out or ask me during office hours or lab. Otherwise, I'll see you then.